Right, we'll get started. Welcome everyone. Unfortunately, Justin woke up feeling a bit crook, so he's asked me to do the introduction for the presentation tonight. Tonight we welcome back Dr Jim Palfreyman, who in 2012 wowed us all with his amazing presentation on his research into pulsars. Tonight he's come back to give us some updates on that research, which I'm sure will be just as amazing. So please extend a warm welcome to Dr. Jim Palfreyman.
Thanks, Phil. And Phil and I worked together many years ago. So I was looking at that. Video, which didn't watch the whole thing, but just a bit of it, 12 years ago, and it was quite interesting. But there was a fairly important moment in there that which I will cover a little bit later on. But so it was prior to a major discovery, not by me, but by other people. But I did talk about it a bit. But I'll come back to that. So back then, in 12 years ago, when I did the presentation that I did, I was at the start of, or in the middle of my masters at the time, and and I was working through, and I was interested in atomic clocks and interested in pulsars, and that's what I did my masters in. And so I've pushed on. I went on and did a PhD, and in the process made a very, very interesting discovery right here in Tasmania, and that's pretty much what I'm going to talk to you about now. But I'm not going to assume that all of those who were here in 12 years ago are here tonight, so I'm going to go back and talk about what a pulsar is, because it's my favourite type of object out there. There's lots of interesting stuff out there, but the thing I really like about these things is that they're different each day you look at them. You know, whereas most things you look at something that doesn't change much for 100 years or 1,000 years or 1,000,000 years, but these things are different every day, which I like. Now, we all know that everything on the internet is true. I got this on the internet, so it's got to be true. You do not really understand something unless you can explain it to your grandmother. So whether Einstein said that or not, I'm not going to enter into that. But it's something that I really enjoy doing, is talking to people at all levels. Be it I've been talking into schools, I've done a presentation at the Jet Propulsion Lab, in front of NASA scientists about my research. So, I've done all levels, and so it's actually really good to come, because I know you guys, know your radio, probably better than, well, almost certainly better than I do. I know quite a little bit about the sort of radio that I work with, but it'll be interesting to have some chats about some of the radio stuff that we do. I promise I'm going to keep the math simple. I actually used that in my PhD. It's the Lobscargill periodogram, for those of you who want to know. It's actually a really, really useful tool. But I'm not going to talk about that tonight. All right. So we've got to talk about, before I can talk about a pulsar, we've got to talk about the life of a star. So a star is born. So you've got this hydrogen floating around, and it clumps together, and the clump gets a little bit bigger, and the gravity gets stronger, and that attracts more hydrogen, and it builds up and up and up. And eventually, this gravitational pressure pushes down, and it gets the gravity is so strong that the core, it begins a nuclear fusion reaction. So the hydrogen atoms get forced together to make helium, and in that process it gives off some energy. And basically you've got the energy pushing out, you've got gravity pulling down, and gravity is relentless. You hear me say this a bit tonight. And the whole thing balances down. You've got the gravity pulling in, the energy pushing out, and it balances down, and you have a star. I just skipped across many, many millions of years there, but we're going quickly. Okay, so that's a nice picture of our sun today. We've actually had some reasonable auroral activity in the last few weeks. Out of curiosity, did anyone get to see the aurora? Can I just have a show of hands, please? I'm really curious. Okay. So, yeah, of course, you would have had a good time. No, back when I was a teenager, I lived at Ferntree, and in that time there was a fantastic aurora, and it's always been the benchmark, and has never been beaten. There was sweeping things across the sky, and it was a really dark sky up there, and it was fantastic. And I've never seen an aurora as good as that. That's always been my benchmark. Well, this one actually beat it. So, you've probably seen a once in a lifetime auroral event there. Okay, so we've got our star. Now eventually the hydrogen runs out in this fusion reaction. Now I'm not going to go into the details of what happens after that, except we've got three options that can happen at this point. Again, I'm jumping over a few 100 million years here, or a certain amount of time, but we've basically got three options. If the star is a small boring star like our sun, then it's actually pretty boring. It's just like a fire going out. It just stops and just fades away, and yeah, not really interesting at all. So yeah. Oh, by the way, it fades away into a white dwarf, and here's a real white dwarf. Now, that star there is the star Sirius, which is the brightest star in the sky. So when you go finish tonight, if the sky's clear, which I don't think it is, you walk outside, you look for the brightest star in the sky, that's Sirius. Now, it has a very small companion, which it's very hard to see, and you need a very, very decent telescope. I've never actually seen Sirius B with my own telescope gear, but it's there. That's a nice little white dwarf. Okay, back to our three options. Small and boring like our sun, just goes out like a fire going out. Next two options are a bit more interesting. If the star is big enough, when the nuclear fusion reaction stops, and it's a big star this time, so gravity wins the battle and down she goes, and again I'm fast forwarding, and you get this massive supernova explosion. Now, at this point, a lot of heavy elements are created. In fact, probably nearly all the elements in this room that you can see came from supernova explosions. And the carbon in your right arm probably came from a different supernova than the carbon in your left arm. What I was scanning around for was any gold and platinum on people's hands and rings and fingers, because that doesn't come from a supernova explosion. Remind me to tell you where that comes from a little later. So we get a supernova. That's actually one of my favourite pictures of a supernova in action. Back to our three options. Big enough to go supernova. If the star is really, really big and the remains collapse down, we'll have an object. Now, everything, I'll just hit pause on that for a minute. Earth has got an escape velocity. If I go outside and throw a rock in the air, it'll come back down. If I can throw a rock at 11 kilometres per second, it will escape Earth's gravity and leave, and that's the escape velocity. Our object here has got an escape velocity greater than the speed of light, and so not even light can escape, which is a bit annoying because we can't see inside it. Now, we can see black holes because as stuff falls into them, it gets very hot, and we can see that heat. So black holes, they're very, very interesting in their own right. There's a massive one at the centre of our galaxy that was imaged recently, but again, we can't see what's going on inside. Now, back to our three options. If we have this Goldilocks-sized star that's big enough to go supernova, but when the remains collapse down after the explosion, what's left has an escape velocity less than the speed of light, we've got something we can see. Now, the gravity is still incredibly strong. It's strong enough to force the electrons in the atoms into the nucleus, and they combine with the protons to form neutrons. And so, basically, it's just a sea of neutrons. Now, this stuff is very dense. So, that I had prepared earlier. If I had a cup full of neutron star material, that cup would weigh as much as Mount Everest. If you took, I read this on the internet, again, must be true, if you took the entire living human population and squashed them down to neutrons, it would be the size of a sugar cube. I did actually check that, I did read it and check, and it is actually about right. So this stuff is really, really, really dense. Now, the neutron star that we've got here is about 20 kilometres across. That's how big they are typically, and weigh about 1.5 to 2 times the mass of the sun. So you've got 1.5 to 2 times the mass of the sun crushed into an object that's 20 kilometres across. It gets better. These objects are massive magnets. The typical typical neutron star has a magnetic field 3 trillion times what we're standing in right now, here on the Earth. And out of the poles, and you can imagine it as, I'm just looking for another prop, this will do. Yeah, okay, that'll do. So imagine there's a bar magnet, you've got a north pole and you've got a south pole, and out of the poles of this magnet streams electromagnetic radiation. gamma rays, X-rays, light, radio waves. Okay, it gets better. This object spins, and when they're first born, they probably spin around 50 times a second and gradually slow down. And as they're spinning, if you here on Earth happen to be in the path of the beam of the magnet, you get to see a brief flash on each rotation. And if that happens, we have what's called a pulsar. Okay, so I've covered most of that. Interestingly, I'll come on to the discovery in a minute, but they were actually predicted to exist in 1934, which was pretty cool. It's a good effort there. So this is where we start to get a little bit interesting now. What's inside one of these things? So we've got these neutrons, but inside there's going to be a lot of pressure going on. And so there's a big question mark as to what's going on in there. You've got this atmosphere, it's called, but it's actually a magnetosphere. Then you've got this crust, and then you've got this superfluid, this outer superfluid core. We'll get onto this, we'll come back to this in a little bit later. We'll fill in some of the pieces there. All right, so I've covered some of that there. We got to the pulsar. Now, pulsars were discovered in 1967 by Jocelyn Bell, and she was a young PhD student. A Nobel Prize was awarded for the discovery of pulsars, justly so. It went to her supervisor, her male supervisor. She missed out. Never fear, Jocelyn's done very well, and has become a professor in physics. She's retired now, still alive, and we're in email conversation every now and again. So she's been to Tassie a few years ago and gave a talk. Now, I said that our pulsar can spin at 50 times a second. Some of them can get sped up. If they're in a binary system, they can get sped up by the other star. I'm not going to go there tonight, but the fastest one we know of spins, I think from memory, 741 times every second. And there's one that's very prominent in the southern sky, which doesn't spin quite that fast, but it will rival atomic clocks in its accuracy, in its spinning, which is pretty amazing.
There's next challenge, Rex.
So,
is that a millipulsar?
Millisecond pulsar, they're called. Yeah. Millisecond pulsar. But we're not going to talk about millisecond pulsars. We're going to now talk about the Vela Pulsar, which is once Jocelyn discovered pulsars, the word went out and everyone started looking for them. And in 1968, they were looking for pulsars, and they found the Vela Pulsar. Now, I'm actually going to tell you a little story about this. And I went to a talk by the guy who discovered it, and I think you folks will really appreciate this story. So, this is back in the day. There's no computers of note. They had pen chart recorders, and it was the type of telescope it was. It wasn't a dish that points. It was sort of like a cross on the ground, and you had to wait for the pulsar to pass overhead, and you'd get a few minutes of the pulse. So they had this pen chart recorder. Now, the Vela Pulsar spins 11 times a second. So the pen was going like that, and they couldn't get the thing rotating fast enough, for the paper coming out fast enough to measure the speed. So this is what they did, and I love this story. So they knew what time it would pass over, and so what they did, they had a pen chart recorder with 2 pens on it, and they got one pen connected to the radio telescope, and the other pen they plugged it into the power point. Maybe through a transformer, but whatever, 50 hertz, okay? And then what they did, so that was going 50 times a second, and then the pulsar came overhead, and this was going 11 roughly, but they didn't know 11 times a second. They unclipped the paper, and the guy sprinted down the hallway as fast as he could go, dragging it out, and they had the reference 50 hertz, even though it was all over the place, and they could compare it to the 11 hertz. And that's how they got the first rotation frequency of the Vela Pulsar. I love that back in 1968. So the discovery of the Vela Pulsar, because it's in the Vela supernova remnant, and so a supernova happened 11,000 years ago, and it's right bang smack in the middle of it. And there's some beautiful photos of the Vela supernova remnant out there, even by amateurs. And so that confirmed the Neutron Star Supernova Association that I just explained to you.
Which telescope was that?
That was Mologolo, was the...
Yes.
Yeah. I'm trying to remember... the papers, Large, Vaughan and Mills. I can't remember which one told the story. I think it was Mills. Anyway, sorry if I'm wrong. Okay, now it turns out it's the brightest pulsar in the sky, the Vela Pulsar, and the second closest. Now, when I say bright, you still need a radio telescope to see it. Okay, but it's quite easily seen in even a small radio telescope, and even again, you'll enjoy this. It's even a target for some very enthusiastic amateur radio people. It's one of the goals is to be able to detect the Vela Pulsar using in your backyard. Steve Olney is a guy who contacted me a few years ago, and he'd set it up in his backyard, and he wanted to get some confirmations of the timings. I was a little sceptical because I thought, well, really, amateur radio, in the backyard? And but no, he's actually done it. And so I'll come back to Steve in a little while because there's a bit of an interesting story coming up on that too. The Vela Pulsar is deep in the southern sky. It passes almost directly overhead each day. And so fortunately, those pesky northerners with their large telescopes can't see it for very long. We're probably in one of the best places in the world to see it. Its pulses change in intensity. Some are brighter than others. Again, I've got something to show you on that too, and I did cover that in my previous talk, so I'm not going to focus so much on that now. But the most important thing that the Vela Pulsar does is it glitches. Now, what's that? So they were watching this pulsar back in 1968, and they'd pass over and they measured it, and it was spinning 11 point blah blah blah, whatever it was, times per second, and they measured it much more accurately using better methods later on. And then they came back one day, and it's gradually slowing down, as I explained, and came back one day, and it was faster than it was the day before. Okay, so that was a puzzle, and that was given the name glitch. And because of the telescope, they had to wait each day for it to pass overhead. And so there was lots of questions there. How quickly did that happen? Did it happen in an hour? Did it happen in a minute? Did it happen in a microsecond? How does something spinning 11 times a second, weighing 1.5 to 2 times the mass of the sun, speed up suddenly? Lots of puzzles. Lots of puzzles.
Was it a permanent speed up or just a temporary?
Good question. So let's if I draw a graph here, I'm going to draw it for me. So here's rotational frequency. Here's time here. Actually, I'll try and do it the other way around for you. Here's rotational frequency here. Here's time here. So it's gradually slowing down, and then it glitches. I've exaggerated. It's a bit smaller than that, but it jumps up like that, and I'll come back to the jump later, and then it comes back to where it was over a period of time of the order of a month or so. Roughly. Well, don't quote me on that one. But so yes, it does come back. And then it glitches again in 3 years' time. So glitches every 3 years, roughly. Unfortunately, it's not predictable, and it's been anything from 18 months to 4 years. It's really hard to predict. So
did they work out how fast the rise time?
Hold that thought. Hold that thought.
Yeah.
Hold that thought. So the problem is we need to look at the pulsar to see the details of the glitch, don't we? You need to be actually looking at it. But you can't predict it, so you can't just grab a large radio telescope like Parkes and say, can I have Parkes for a year and stare at one pulsar hoping to catch a glitch? Sorry, it doesn't work like that. Other people want to use these telescopes, and so it becomes tricky. You can sort of make a guess as when the glitch might be, grab the telescope or have it for a week or two, and people did try various telescopes to do that, and they all failed. Okay, you may be getting where this is going. So the typical speed up is around 3 parts per million. Doesn't sound like much, but we're comparing this to an atomic clock, and that's for a neutron star the size it is, spinning as fast it is. That's actually pretty large. So the current hypothesis is that, there's the text, the vortices that are pinned in the crust get separated by the magnetosphere. So I'm going to just dial this back, and let's try and keep it a bit sort of more straightforward and something that we can all relate to maybe. So I want you to think of the pulsar as having a hard crust and a superfluid core, which I mentioned before. So on the crust on the outside, that's the bit with the magnetic field, and that's the bit that's slowing down. Now, being a superfluid core, it has no friction. And so it rotates independently of the crust. So the crust is slowing down, but the core is maintaining the same speed. Now, after 3 years, roughly, the difference between those two gets too great, and this stuff, which is actually quite complex, happens inside, but basically the core grips the crust, speeds it up, and then lets go, and then it starts the process again. So that was the hypothesis. That was made in Anderson and Ito, I think, made that hypothesis in the 80s. Okay, so it was obviously important to catch glitches live. That's what we wanted to do. Now, here in Tassie, a project was set up by Peter McCulloch and other people at the university to build a dedicated Vela telescope to look at the Vela Pulsar and catch a glitch. That's what they wanted to do. And they built a 14-metre radio telescope, and they did catch a glitch, or possibly two. But the fact it was only 14 metres across meant they weren't able to see the individual pulses. They knew the rotation rate of the pulsar, and they had to sort of average the pulses over 30 seconds, and then they'd see the change in time as the glitch happened, but they couldn't see the individual pulses. So they knew that the glitch happened in under 30 seconds, partly answer your question, but it wasn't enough resolution to do it. So you need a large radio telescope to see the individual pulses. I wrote this slide, I actually wrote a little while ago, and it still hasn't changed. Glitches have only been caught live here in Hobart, with one exception. I've got except for Steve Olney there, so I will come back to that. Don't let me forget. So the big question is, as was pointed out, how long did it take to speed up? That's just a cool picture I really like. That's a picture of the Vela Pulsar in X-rays. And I'll point here. See, the pulsar is right there in the middle, and it's just got this lovely sort of, I don't know what you'd call that, sort of like a carousel around it, and then you've got this stream coming out here that wobbles. There's a video of this on the internet. You can go and look that one up, and you can see it wobbling. It actually looks really cool. But I just like the picture, so I've just put that there.
Doesn't the axis have to point to us?
It does. That's
so
okay.
How can we have a picture of that?
No. Okay, good. You've actually picked on something that's really important. So the rotational axis, which is that line there, which is definitely not pointing at us. Back to our magnetic field. The rotational axis doesn't necessarily. So you might get a pulse here, but the rotational axis is that way. Okay, and as pulsars age, in fact, the magnet moves up and up and up, and eventually they become aligned, and then they're no longer a pulsar.
So the pulse doesn't come out of the axis?
No,
okay.
no, not the rotational axis. It comes out of the magnetic axis.
Okay.
They're two separate things. So here on Earth, we sort of roughly think that the magnetic axis and the rotational axis are roughly the same. They're not actually. They're quite a few degrees apart. They're roughly close, but quite a few degrees apart. But yeah, so the pulsar, it could be 90 degrees, or it could be 0, or anything in between.
Okay.
Yep.
So if you're pointing at it, you'll see that, and if you've got that antenna, you'll see it all the time.
Yes.
Yeah.
There. So there's the antenna that we use. That's the Mount Pleasant 26 metre. I observe it. I'll dive into some details here. 1376 megahertz is the the radio frequency that I have done most of my observations at. Excuse me. Now,
Big chords?
you're jumping the gun. I was about to explain that. So, okay, so with pulsars, and particularly the Vela Pulsar, it's basically the higher the frequency, the less flux density is, so the fainter it is. So the lower the frequency, the brighter it is. So you'd sort of think, well, let's go down into the low frequencies. That would make sense. So putting aside RFI and stuff like that, which is a major issue we have to deal with at Mount Pleasant because we're close to the city and the airport and everything like that. You also get another problem is that between us and the pulsar, you'd think there's a vacuum. And there is pretty much a vacuum, but it's not a perfect vacuum. There is stuff between us and the pulsar. And the radio waves, the pulses, get sort of reflected around on this stuff, and they get smeared out. So the lower the frequency you get, the pulse, and I'll show you the pulse in a minute, the pulses get smeared out. The higher the frequencies you go, you get more resolution, if you like, or more crisp pulse, but because the reflections aren't happening as much, but the flux density is less, and so it's harder to pick up, and so you need a better telescope. So you've got to try and find this balance between getting the best pulse shape and getting the brightest pulse that you can, and staying away from RFI. So that's the other big thing, of course. So 1370, I originally started at 1440 and megahertz, and that was good. When I last spoke here, I was at 1440, and then I came in one day and turned it on, and it was rubbish. It was completely destroyed because of RFI, and it turns out a new transmitter had just been turned on. I think the one you and I were just talking about before, Phil. And so it blew me out of the water, so I had to move frequencies to avoid it. Fortunately, that 1376 has stood the test of time, which has been good. So while I was doing my PhD, I was basically getting as much time as I could on the antenna, and when I get a full day, I could observe 19 hours per day, because the Vela Pulsar from rise to set is 19 hours here in Hobart, which is quite decent. Even though this is going back a few years now, I was recording 640 megabytes every 10 seconds, which is still a reasonable decent amount of data. 4 terabytes of data collected every day. Collected over 3 and processed over 3 petabytes of data. Says 15,600 hours. That's well over 16,000 now, and that at the time 600 million pulses. So if you think about it, if it's up 19 hours, and if I had 100% access to the telescope, there's only 5 hours in the day that I wouldn't be able to catch it if the glitch happened, and that was pretty good odds. Mind you, I still had to fight others for the telescope time. So I couldn't focus my entire PhD on the glitch, because if I missed it for whatever reason, I needed other stuff as well. So I did cover other things in my thesis as well. However, before I go on, who's been to Mount Pleasant for a tour and seen this control room? Just put your hands up. Okay, cool, excellent.
We've got to borrow it.
Sorry?
We've got to borrow it.
I saw the video of that the other day.
Have to borrow it again.
Yeah.
I
we
did.
got signals to the moon and back.
Yeah.
3 milliwatt.
Yeah, I saw that. Yeah, I looked that up. I can't remember why I stumbled on it, and it was really cool.
I sent it to you.
Oh, you sent it to me. That's where it came from. Yeah. So that's the control room. Honestly, it hasn't changed much in ages. We've thrown out some of the really old equipment now, or put it away in storage.
CRT.
Yeah, that's gone. Yeah, we don't have the CRT anymore. I don't know if you can see it, but just there, that's the pin chart recorder. I did actually get it going for old time's sake a number of years ago with the Vela Pulsar, because I just wanted to see the pen doing that thing. And but it sort of doesn't work much now anymore, so we don't use it. But it's still there just because it looks good. I like it. Out the back, we've got a couple of hydrogen mazes out the back of the place, but this is the one I like. This is the NASA's NR11. It's an atomic clock. Currently, as we're saying at the moment, it's accuracy of about 1 second every 250 million years. I did talk about that in the last talk. I just put it there because it was there.
What's that in parts per million?
Oh, look, if you sit there watching, it's in the order of nanoseconds a day, billionths of a second a day.
With our GPS clocks, we get about 1 part per 10 billion. 10 billion, yeah.
So just to explain, the GPS, as you know, you can use it as a clock.
Yeah.
And it does a pretty good job, but it varies throughout the day. And you guys probably know more about it than I do, but I think it's to do with the ionosphere and the signals coming down.
It is.
Yeah. And so what we now, and cesium, which is the basis for many of the atomic clocks on the GPS, that's our standard for the second, and over a long period of time, that is a really good reference. But over a short period of time, even putting aside the ionosphere, it jitters around a bit. It's not good over a few hours. Hydrogen masers go back to that. Hydrogen masers are fantastic over a few hours, even up to a day. Like they're so solid and so steady, better than even a cesium clock. And so if your ideal thing is if you have your hydrogen maser and then you sort of steer it and guide it using the GPS. So what I do is I compare the GPS to the hydrogen maser, and it's wibble wobbling all over the place when I say, of the order of what you spoke about. But over a period of a month or two, if I see it's drifted, a few tens or 15 nanoseconds, I can adjust it and so bring it slowly back. Yeah. And so over short observing times, like a day or less, the hydrogen maser is the best atomic clock to have, and it's vaguely affordable compared to some of the more expensive, more accurate ones. Anyway, I covered all that in my last talk, so if you want to find out more about that, go and check out the video on that one. Okay, so if we take the Vela Pulsar and observe it for 19 hours at 1376 megahertz, and add up all the pulses, because there's a lot of noise going along. There's even in the atmosphere and even in the atmosphere of the pulsar itself, and in between us and the pulsar, there's lots of noise happening, and there's noise in the telescope, electrical noise. But if you summarise a day's worth of pulses and average them all up, that's what the pulse looks like. Just take a note of that middle line. I'll come back to that.
Is that the amplitude of the pulse?
Yes, so that's correct. So we've got time here on the x-axis. I'm sorry, I've looked at this graph, so many times. It's just I just see it like it's a photo of my children or something like that. It's just I should have explained the axes and what it is. So apologies for that. So on the x-axis we've got time, and that's in milliseconds. So 0 lines up with the peak of the pulse there, and the y-axis is relative flux density, and I've just made the maximum 1. So the red line marks the halfway mark, and you can see that there's sort of an emission sort of there. There's a little lump there, and if you can imagine it as a Gaussian curve, like that sort of shape, is each emission. You've got one here, big one here. If you look very carefully, there's a tiny little dent where the cursor is there, and there's another emission zone there, and there's 3 of them. There's possibly even a 4th out the front for brighter pulses, but anyway. Okay.
So if it was a spec out and you had a higher resolution bandwidth, you could see the individual pulses.
So, yes and no, and I've got something to show you that, hold that thought. I've got something to come back to you on that one. So we're doing, so I talked about the glitch. So I was grabbing as much telescope time as I possibly could, and I'd set up a little thing that every 15 minutes it would take one of the 10-second files, process it, analyse it, check the timings and see if a glitch has occurred, and if it did, it would send me a text on my mobile. And that worked. I got lots of false alarms, probably once or twice a month I get a false alarm. So anyway, it was 9:30 at night on the 12th of December 2016, and I was getting sort of a bit tired and getting ready for bed, and my phone goes off. I thought, oh. And they're the texts. And then I sort of looked and I thought, oh, I better check this out. And then I got another text 15 minutes later, and I sat down and ran another run. And back then it would take about 15 minutes, 10 to 15 minutes to process a 10-second file on the computers I had back then. A lot faster now. And it looked like it had glitched. There was no RFI. I thought, it's happened. And so that was exciting. That was very exciting. And I didn't actually go to bed that night. I sat there processing. So the glitch, so that was the first glitch caught in the history of pulsars with a telescope large enough to see individual pulses. So the magnitude, it wasn't as big as a typical glitch. It was sort of 1.5 parts per million. And we've also, UTAS runs a number of radio telescopes around Australia. The other one we operate, the other big one, is the Sejuna telescope in South Australia. It's a 30-metre telescope. its receiver, our receiver here is cooled, so we cool it down to about 20 Kelvin, 20 degrees above absolute zero. And the one at Sejuna, same frequency L band, but it wasn't cooled. So we actually get better results in Hobart with a slightly smaller telescope because of the cooling factor. And when the glitch happened, some weird stuff happened. So that's a technical astrophysics term, so let's have a look. So that's probably, it's not the prettiest plot I've ever done, but it's my favourite plot I've ever done, that's for sure. Each dot there is an individual pulse on the Vela Pulsar, and that you can see where the glitch is. So we've got arrival time, and that's about 72 minutes from here to here, a bit over an hour. And 0 is, this is the residual, so that's observed minus predicted. And so pulsars spin very accurately in the short term, and so you can predict when a pulse is going to arrive. And so I had the ephemeris, as we call it, in place, and you can see the pulses are arriving on average right on when they're supposed to. There's variation because there's lots of noise, as I mentioned before. And then suddenly the glitch happens, and so it speeds up, so they're arriving earlier, hence the negative times. So the cool stuff happens right in there. So going back to the question you asked before about how quick, we need to dive in and have a look what's going on in there. Now, before we do that, some weird stuff did happen. So these are some individual pulses, okay, from the pulsar. So there's the average pulse at the bottom there. And I'll just pick the one above it there. That's what sort of a typical individual pulse would look like. Now, there's a lot of noise built in there. That's why it looks a little bit different from the average pulse. They average up to the average pulse that I showed you before and what is on the bottom of the diagram. But each individual pulse is a little bit different. But look what happened right there. Pulse 77 when the glitch happened. Flatlined, nothing. No pulse at all. Now,
what's the time resolution between each of those graphs?
So it's 11 times a second, so 89 milliseconds is,
I see.
yeah. So
it's just between one pulse and the next one.
Yes, exactly. And now you're not seeing the whole pulse period there because there's a lot of nothing happening because the pulse is about 5 milliseconds wide. It's 89 millisecond period, so there's a lot of nothing that I've left out on the sides, but it's centered. But you can see from there to there, you probably can't see, but that says -5 and that's 0 and then 5. So it's about 10 milliseconds from there to there. So all of a sudden, going up the page, so pulse, 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 and then all of a sudden you get this really wide pulse, okay, which is unusual, and then we get a null. And then it looks like it's back to normal. Now we'll get to the red in a minute. You folks will know what I'm talking about, which is really lovely. Vela is highly linearly polarised, like nearly all linear polarised. And so what we're looking at in red now is the linear polarisation of the pulsar, and you can see it's almost the same in linear as it is in full intensity for the integrated pulse. And then for each of these pulses, they look roughly the same. And even this big wide pulse is very similar. And then we've got our flat line. But then here, we've got what's looked like it's come back online and is doing anything, but there's no linear polarization signal at all for 2 pulses. And then even this one's not quite back, and then she gets sort of back on track after that. So
Black's circular, is it?
No, black is total intensity.
What polarization?
You're combining all everything combined, linear, circular, the lot, just the total intensity. And we split it down to, we use a thing called Stokes parameters, so we split it down into linear and circular. And there's not much circular with coming from the Vela Pulsar at all. There's a tiny bit, but not much. And we observe with 2 linear receivers in L band, but in some of our other receivers we've got circulars as well. So bottom line is though, it missed a beat and everything went wacky. Now, we're talking about a magnetic field that's 3 trillion times the magnetic field of the Earth, and the star the size it is, suddenly its magnetic field, its magnetosphere, just suddenly went weird.
Can I ask you a question, please? You were saying earlier that the actual magnetic radiation comes out from the surface of the pulsar. So
Comes from the poles of the, yeah.
Does it actually radiate from the core out and through, or does it radiate off the surface from the intensity?
Okay, we're now going down into deep and unknown territory, because the emission mechanism of pulsars is not that well understood. It's reasonably well understood, but not that well understood.
So you have to say there's a disconnect then between the core, or the source of generating the energy, and the actual radiating element, which is the surface of it.
Mm.
And
So, yeah.
So you sort of think in terms of radio that there's some pretty interesting activities happening within the core.
Yeah. And why the core should affect the crust and the emission is a good question. It's opened a lot of questions. You know, there's a lot of questions being asked in this observation, and we still don't know the answer to lots of them.
So you said the outer crust can spin independently of the core, and seeing it's highly magnetic, would it be as simple as you've got, say, like a bloody big asteroid or something that got pulled in towards it, and it actually hit the outer crust and knocked it?
You know, there's heaps of ideas have been thrown around. So if you've got the idea of a collision or something like that could do it, that's a reasonable thing. But why every 3 years? And why not exactly every 3 years? So if it was something orbiting really close, you'd expect it to be very predictable. Especially we've been observing it for 50 years. We'd have it down pat by now. And it's not just the odd random event. You know, once happens one day, and then another in a year, and another in 5, and then another in 3, and all over the place to indicate sort of random events. It's too predictable, but annoyingly not predictable enough.
Could it be like sunspots, because the sun is a great, incredibly magnetised plasma.
Yep.
And it could be going. I don't understand fluid dynamics particularly well, but it's almost like going from a sufficient differential shift that goes from linear to laminar to turbulent flow, and it's a magnetic liquid, so it's all coupling.
Could be. It could be.
Some pretty interesting magnetohydrodynamics going on.
There is an incredible amount of stuff, and we will cover some of that. Not that sort of stuff, but some of the people who've taken some of my work. So hold that thought, because it is super interesting. But I hope you can appreciate the importance of those few crucial seconds that I happened to catch and what it showed. Now,
how did you number them?
Arbitrarily? It's arbitrary, yeah. So each file is 10 seconds. Okay. Arbitrary 10 seconds, 111 pulses per file, and they get numbered from 0 to 110. So it's for my reference. Each is it there in the notes? It's on the right, but each file has a name, and the name is the date and time it was recorded, and so it's Pulse 77 in such and such a file on the 16th of December. 12th of December, 16th of December.
Can we go back to the one before?
This one.
Now, is that drop is a drop in the speed?
Yes. Speed. No, it's dropping the residual, so it's arriving earlier because it's spinning faster.
Right. So it's spinning faster.
Yep.
So if we were talking about speed, it would go up.
Yes, but we're not talking rotation. We're not talking in hertz. We're talking in arrival times of the pulses, and they're arriving. It's sped up, so the pulse is coming a bit earlier. So the arrival is earlier than predicted.
This is eventually a phase shift, isn't it?
Yes.
So there seems to be a lot of points on that downslope, but they're rare glitches. So how have you got so many?
The glitch is just one or two
the
things.
The glitch is an event that's sped up the pulsar, okay, and there's a prediction that the pulsars are going to arrive at this time. Let's pretend they're going to arrive once every second. Now the thing's suddenly sped up, like a clock's going faster. It's arrived before I'm predicting it, so it goes down, and then the next time round it's earlier again, and earlier again, and earlier again.
It's sped up.
Yeah. So imagine if you had two clocks, one's faster than the other. they're going to get worse and worse and worse if you look at the difference between the two.
So when you were processing those files that night, how excited were you when you saw it pop up? Or how frustrated were you that it took so long to pop up?
So I rapidly started processing. Of course, I had to do the calculation of when the glitch occurred, and then I roughly knew, and I was scanning through the files, and then I looked at the file, the 10-second file, and each of the individual pulses on it, and I saw effectively that where the cursor is the flat line, the null, and it was like, am I really seeing this? And I sent it off to my supervisor and showed him, and he said, that looks like a null. Now, can I just point out, old pulsars, null. It's a well-known thing that if you've got a very old pulsar near the end of its life, they skip beats all the time. That's nothing new. But Vela, Vela is a young pulsar. It's only 10 or 11,000 years old. It's a baby, and has never been known to null. And hey, I had some data, so I went looking. I went seriously looking for nulls in the data I had, and couldn't find one. And in fact, we're still looking to finding different ways to tease the data apart to look for nulls. But no, we've never found one other than that one. So something big happened. So there was a question there about the emission. So if you're staring down the barrel of the magnet, so there, let's pretend you're staring down one of the poles of the magnet as it's sweeping across Earth. You can see, it's a bit hard to read, isn't it? Because it's highly linear polarised, you'll see that as the Earth sweeps, if you imagine because it's sweeping like that from the Earth's perspective, it's like drawing a line across these field lines here. And so the linear polarisation, the angle of the linear polarisation changes as it sweeps. And you get this, depending on the pulsar, you get this sort of sweep S shape. Now, go back to here, that's what this column is here. So for the integrated pulse, you can see what for the Vela Pulsar, what that linear rotation looks like. And you can just see it barely in some of these pulses here, and then that vanishes as well when the linear polarisation vanished. All right, let's do what they do in the movies and go enhance. Let's dive in where all the action happens. So this is the same plot as that one, but we're zooming right into the interesting part. So you can't see the glitch. You can't see the change here because we've zoomed in right to where the action is. It's barely detectable at this point. But TG, that point there, that's the predicted time of the glitch. So if you look at all the times leading up to the glitch and come back and look at all the times after the glitch and cross the lines over, where do they meet? And because we've got a lot of data there, we can nail that down very, very accurately. That's where they meet at that point, at that line TG. And the error bar at the top tells you what the error is in that process. Now, the null happened here, just a little bit before, or within the error bar. So we called the null T0. We labelled that as we'll call that that's when the glitch actually happened. Now we don't have a time for it because it didn't pulse. So I've just had to put the point actually on the red line, but we know the time that it happened, which is along the x-axis. But the residual, there was no residual because it didn't pulse. So we've just pretended it had a residual of 0. Now, you can look at the scale here. You've got, by the way, barycentric arrival time. In pulsar astrophysics, we always use the arrival time at the barycenter of the solar system, which is inside the sun. It's the gravitational centre of the whole solar system. So we reduce everything back to that point because someone observing in South Africa, observing these same pulses, would see arrival times slightly different from mine because of the rotation of the Earth and the orbit of the Earth and all that sort of stuff. And so to solve all that, we reduce everything back to the barycentric arrival time, or when it would arrive at the gravitational centre of the solar system, which you can think of as the sun. It's not quite, but very close. So you can see that that's about 5 seconds there. And just before that, you can see I've made it a line graph this time, not a scatter graph. And so you can see that what it was looking like. And then just when the null happened, we've got this large variation here, which is, okay, that could be just a fluke. And then, look here what happened here. Suddenly the pulses were arriving later, briefly, but the variance, as in how much they were varying, got very narrow for a really long period of time. And I marked those as T1 and T2 as the beginning and end, so something weird was happening there.
So the core was locking, the outer was locking to the core.
So all the action that was happening, happened fairly quickly, and we'll get back to that. But some weird stuff was happening while it was happening, and yes, it's possibly related to the core. Certainly, I've got slides on it, so just hold that thought again. I'm just conscious of time too. Am I all right kicking on? It's 20 past.
You're
Fine? Cool. So because of that, I decided to plot a graph of mean versus standard deviation of every point on that graph you just saw. Well, not on that graph, but on that 72-minute plot. So as compared to the residual. And you'd expect just a general round splodge, just like if you just had a target on the ground and were dropping objects on it, it would sort of mainly be on the target and a few would be off. But then this part here, that part here between T1 and T2, you can see they wander off well out of what you'd expect. So that's, again, something weird. Other weird things I'm going to show you here. So again, this is in seconds along the x-axis here is about 3,500 seconds. Actually, it's probably an hour. Yes, probably an hour. And this is just the peak flux density, not on individual pulses, but for certain time frames. I can't recall whether it was probably minutes, maybe 60. No, it'd be more than that. Maybe every 10 seconds. Anyway, it's the average flux density for a bunch of pulses, and you can see it's all hovering along before, and then as the glitch happens, it drops right back. And that's an average. That must be sort of 360 dots there. It'd be 10 each of the 10-second files. That's what that would be. So the flux density also dropped on average right across the board. And now we're not talking just seconds or barely seconds. We're talking multiple tens of seconds or even up in the minute range. So again, a bit odd. Okay. I said I was recording at Ceduna as well, the other telescope, at the same time. You beauty, I thought. So couldn't wait to get that data down, but to get that data back, we have one now, but no fibre cable there. The internet connection we had there was really slow, so basically had to put the discs, ship them by post and get them back. So I didn't get this data for a while. And I processed it and popped it up, and look what I got there. Now, the individual pulses at Ceduna weren't anywhere near as good as what it was at Mount Pleasant, so these are the 10-second averages. But look at this gap. What the hell happened there? Would you believe it? It was a cable. So we got in the telescope, it's a telescope that rotates around like this. And in the twister where the cables go up, it had twisted around, and one of the twisted pair, one of the B and C had just slightly come undone and lost. We lost signal. You wouldn't believe it, would you? But it sort of almost connected itself and got back together just for the glitch, but not quite. So anyway, how's that for luck?
Murphy's Law.
Murphy's Law, yes, yeah. Okay, so how long did it take to speed up? Now, what I'm about to show you now is probably a slightly incorrect time, because I think we might have revised it since I did that slide, and but it's reasonably close. So from my data, I said about 5 seconds. We've sort of looked at it, and I'll show you what we're going to talk about now as some other people joined in with some of my data and examined it in much more detail, and have revised that, I think, to 12 seconds. But yeah, that sort of order anyway. It's still quick. All right, so I got contacted by the way, that all that I've just showed you up until there, that got published, and that got published in Nature, which is arguably the top journal on the planet, and they loved articles like this. It was very hard to get in. Like, I submitted it, and they said, "Yep, this looks great, but you need to do more work on the polarisation," because I hadn't done any polarisation work at all, because I just wanted to get this out. Now, I then had to bring in another collaborator who was an expert, world expert on polarisation, and get him to calibrate it and do all that sort of stuff. And it actually made the paper 3 times as good. And some of the stuff I talked about with polarisation, that wasn't there in the original paper. So I got pushed back. It took another 9 months of work to do it, but eventually it came through. And so anyway, once it was published, some further people contacted me and wanted to have my data so they could dive in from a theoretical perspective and let's have a closer look. So, and they did a really good job. And as when you share data as a scientist, you get co-author. You go as a co-author on the paper, which is good. And it was good to have other people with different skill sets than me diving in and looking at the hardcore theories of the internals of neutron stars, which, believe me, is not an easy topic. So this was Greig's plot. Now here we've got frequency. So we were talking about residual before. Now we're talking about frequency. So how fast it's going. So it's humming along and then it speeds up. Okay, and you can see that it jumps up, and you can notice that it sort of overshoots at the top. And we have known about that before. We actually, Peter McCulloch and co, who saw the glitch in the 14 metre, they saw that slight overshoot, and that was sort of part of the theory of the rotating superfluid core, the separate rotating cores. That overshoot sort of ties in with that theory. But what Greg and others found out, Greg Ashton and others found out, was notice there was a little dip just before, which no one had seen before. So that was interesting. So what's that mean? So his interpretation, or their interpretation, means that there's another core inside the superfluid core rotating independently as well. So you've got these multi-layers of cores. That's it's amazing all that comes from barely 20 seconds worth of data from little old Mount Pleasant radio telescope just around the corner. Okay. Can we predict a glitch? If we could predict a glitch down to even the week, that would be awesome, because we just get every radio telescope, even the ones doing gamma ray and X-ray observing, orbiting the Earth, get them all to point at the Vela Pulsar for a week, and we'd have a fantastic data set. So being able to predict a glitch would be really, really great. Now, this is out of my thesis. So one of the things I noticed, so what we've got here, remember I showed you the pulse before, and I showed you the width, the red line with the width, and that was the 50% level, the width of the pulse at the halfway mark. So over 19 hours, I can measure that really, really accurately. And then what I did was plot that width over time, and that's what each one of those dots are. So you can see the width varies over time. Now, the x-axis is modified Julian date, so that's the number of days since, I can't even remember the date, but it's like 1898 or something, some day back then. So basically we're in days along there, and astronomers use that because it takes into account no daylight saving, no time zones. We took in universal time, of course, and so it's days on the x-axis. So anyway, look at the pattern. You'll see that there's this sort of gets wider and then gets narrow again, and wide and narrow. Now the red lines that are there, they're what's called micro glitches. So Vela is a very noisy pulsar. It's not a good clock compared to an atomic clock. It's pretty rubbish actually. And it varies all the time, and sometimes it has what we call micro glitches, which is not a glitch that happens in 10 seconds or so, but over a period of days it speeds up just a little bit. So it's got all this timing noise. And I've marked those with the red lines, which we can see in the timing data. And you can see there's this sort of, the pulse width gets narrower, not by much. Notice we're talking milliseconds here, and that's 1.52 milliseconds, and that's 1.50 milliseconds. So the width change is very, very tight, but because I'm observing over 19 hours, I can measure it at that accuracy. And so that sort of looked like, if the pulse is getting narrower, it might be a hint that there's a glitch about to happen. We can sort of predict micro glitches. Maybe it will predict the big glitch. So that was my hope. So there we go. Then the big glitch comes along. So you see all the micro glitches happens at the dip, and then the big glitch happens that I caught, and it happened at a maximum. So it blew that out of the water completely. That's science for you, you know.
So they're unrelated.
Yeah, well, maybe. The interesting thing was, look, it happened at a maximum. Maybe that's the thing.
Do we understand anything about the fluid dynamics of how the actual star operates?
The neutron star.
Yeah.
When you say we, you mean
we collectively.
we collectively on Earth.
Yes.
There are the collaborators I talked about before I showed you their data. People like that, yes, they've and there's theoreticians love neutron stars because they can do that sort of hardcore mathematics, and then data like this, because it's pulsing, we can get very, very accurate rotational data, which is and again I've got a slide on this coming up saying, well, what's the point of all this in the big picture? So let me come to that slide. So can we predict a glitch? No, but I'm working on it. So why? Who really cares? What's the point of this? Now, the thing about this neutron star, it's 1,000 light years away. So that, by the way, that glitch happened 1,000 years ago, really, and every 3 years roughly. So what's there? 330 odd glitches have already happened and are on their way to us. So they're in the past and in our future at the same time. But the neutron star environment is a laboratory that we can't create here on Earth. It's too intense. That magnetic field, that gravity, the heat, the superfluid, everything. It's a laboratory that we cannot recreate here on Earth. So it does help us understand how matter behaves, the equation of state. So for example, liquid at 0 degrees is frozen, and at 100 degrees it's a gas, and in between it's a liquid. That's the equation of state. But what happens when you have these incredible temperatures and pressures like in a neutron star? So the theoreticians love neutron stars because they can make some theories about it and work out what's going to happen at these temperatures and pressures, and then hopefully observations like this can give them some understanding. Might help with nuclear fusion for us to generate power without radioactivity. Who knows? I always think back to relativity, the MRIs and Wi-Fi were all sort of outputs from studies like this. So for example, Wi-Fi was, that became from radio astronomy, and the MRI, magnetic resonance imaging, was all about studying how things behave, how water behaves in a very, very strong magnetic field, and that turns into a very, very useful tool. And relativity, of course, I'm sure you lot are aware that the clocks on the GPS are actually running deliberately fast because general relativity, because they have a lower gravity up there orbiting the Earth, they have to run them deliberately faster so they keep proper time. If Einstein hadn't done relativity, your GPSs wouldn't work. Gravitational waves. So in my last talk, it was 12 years ago, I mentioned we were trying to discover gravitational waves using pulsars. And I say we, it wasn't me personally, but scientists in our field. And there was a bit of a race on with people developing this laser interferometer, which they named LIGO, to try and find gravitational waves as well. And back then it was a race. Who was going to discover them first? Well, LIGO won that race. They discovered gravitational waves and appropriate Nobel Prizes were awarded. Since then, I have a link to LIGO, and I've been lucky enough to be co-author on a few of their papers. We've been looking for gravitational waves from pulsars. So the idea is that this pulsar is spinning, right? Now, if, let's say, it's got a little lump on its side, I'll call it a mountain. It is way as much as a mountain, but it might only be this big, but it would generate gravitational waves. And if we observe over a long period of time, because they're not big like black holes colliding, they're very tiny, but they're very accurately predicted, and especially if you've got a radio telescope that knows precisely how fast the pulsar is spinning at any given time, they can average over a long, long period of time and hopefully see a gravitational wave. And we've been trying this for years now, and we've had a few failures, and we published the failures. When I say we, they, and I I joined them on the paper, but we're still looking. They've recently upgraded the detectors, and we're still continuously looking for that. So that'd be an exciting one if that ever happens. And we did look for a gravitational wave from the glitch as well, and it didn't happen, unfortunately. But with the detectors they had back then. I just have to put that up because that was a letter I got from Nature saying we've accepted your publication, and that was a really nice moment, I must say. That was one of the best emails I've ever received. So much work went just to get that. All right. Did I cover? No, I forgot. I've got to show you a cool graph. Right. So Phil asked me before, how do we know the distances between stuff? Now, and I mentioned before, I think it was to you, about how there's stuff between us and the pulsar that when the pulse comes in, it smears it out. It also slows down the pulse. So the higher frequencies get slowed down less than the lower frequencies. We call it dispersion measure. So basically, when a pulse arrives from the Vela Pulsar, the higher frequencies arrive first. So let's go right to the top of the spectrum. The gamma rays and X-rays will arrive first. And then as we go down the spectrum, they will arrive later. Light is up there as well, of course, but when we get into radio, even with a bandwidth of 64 megahertz, we can see the difference between the high frequency arriving and the low frequency. That's the bandwidth I used, by the way. I don't know if I said that.
How many microseconds or whatever?
Would you like to see it happen live?
All right.
Not live, but a video. So this is a video that's only appreciated by people like yourselves. So I'll just explain. Let's move that back. Okay. So first of all, Vela emits pulses, as I said, but it occasionally emits bright pulses, right? And you saw the scale of the average pulse before. I had it as a 1. Over all those pulses that I've observed, I've seen some very, very bright pulses. So the brightest one was 130 times brighter than the normal pulse, which was, it was absolutely out of this world. And so I did quite a bit of analysis in my thesis on that particular pulse because it was so bright. But one thing I liked about it, what I did was replay the arrival of this pulse. And to answer your questions, in the order of milliseconds is the difference. So what we've got here is a spectrum analyzer effectively. Okay, so you've got frequency along the x-axis. We've got two channels, so you're pretty much going to see the same thing in the same channel. And on the y-axis, you've got intensity. Okay, now we're playing through time as I play this. I don't know how long the video is. What's it? 5 seconds, so it's quick. And I'll play it again if you want to see it. But what you're seeing, and prior to, as soon as I hit play, you're seeing normal pulses, and you can't see them because they're too faint. It's only when we take those frequency, that 64 megahertz, and line up the different arrival times. So we slow down the high frequencies and speed up the lower frequencies, add them all together, get rid of the polarization and get intensity, and then we can see the pulse a lot easier. So you're seeing like raw data off the telescope at this point, recorded. So normally you don't see anything, but this pulse is so bright you can see it. So have a look. Did you see that? So that was the bright pulse arriving. It's high on the left, sorry about that, because we reverse when we bring it down and mix it. So you saw the pulse, the high frequency arrived first, and then I'll replay it again for you. There we go. Did you see it? So you saw this. No. I'll pause it for you.
Oh, right there it was. Yeah. Come on, it's easy to be quick.
There we go. Caught it. So, and you'll see it's sweeping across in frequency. Yeah.
That's that little shit that goes up HF.
So anyway, you folks would appreciate that plot. There's not many people who do in my public talks. So anyway, thank you very much. Any questions? You've been pumping away all night, so probably not.
A slightly tangential question. Our favourite scientist for ham radio is Joe Taylor.
Oh yeah.
And who's done a lot of work on
Very famous name in my field. Yeah.
Now, he got his Nobel Prize in the same field, didn't he? I wonder if you can explain what he did that got him a Nobel Prize.
Okay, so I caught a bit off guard there, so I'm going to go from memory, but it was, I think, Holson Taylor, they discovered a binary pulsar system orbiting, and one of them was a pulsar, and I think it was, they could see the orbit decaying and changing, and that was due to the gravitational waves being emitted, I think, or the gravitational radiation being emitted, and so that proved Einstein's general relativity. There you go. That's my off the cuff thing, but yeah, he's one of our most famous pulsar scientists, that's for sure. Yeah. Yeah.
It's pretty famous in our field too.
I don't know if I quite got this right, but going right back to the start, pulsars are a subset of neutron stars?
Yes.
So are all neutron stars pulsars, just we're in the wrong spot? Or not? Almost. So in general, yes. So Vela's a pulsar for us. For someone in another part of the galaxy, no, probably not. But pulsars, remember I said that the magnetic field, there's the rotation field and there's the magnetic field. Over time, they sort of become what's called an aligned rotator. And so they are a neutron star still, but they're not pulsing for anybody. It's just glowing out in one spot. So if you were up there, you'd see the signal, but it wouldn't pulse. Yeah. It would be all the time. And if you're down here, you'd never see it. So you're almost spot on there, but just in that one exception. Okay. Yeah. With the situation occurring inside the star, and what you're saying about the slippage on the surface, because we really have no idea of what's going on, we know it's like a massive furnace and all these superheated materials. If when the slippage occurred, for example, its magnetic field internally collapsed or something changed substantially, it could well be that the material changes phase, and you get a lock up between, like the reverse of slippage, and so it locks up and then it accelerates, because you see this overshoot, and then as the situation comes back to normal and temperatures or the energy goes back to its normal role, then it continues on because of the mass relationship between the core and the outside. You sort of think, it sounds absolutely astounding that could happen in that time, but the thing is so much bigger than anything that we understand, and there's that many sort of functions taking place. Who knows? But it's pretty substantial when you think about to try and actually speed something up and then shut it down in that short period of time. It weighs mega mass.
That's correct, and the answer is we don't know. It's still a very much an open field. Now, briefly, I need to, if you've done your maths correctly in your head, this happened in 2016, I published in Nature in 2018. So what's happened since then with glitches? If you add it up, 2016, well, what happened in 2019? Well, the thing is, the bloody thing arrived a year early, didn't it? And it was right near Christmas in the new year. Everyone the world over was snoozing and enjoying the summer break, and no one caught that glitch.
How do you know it arrived early?
Well, after the event,
so people were monitoring.
No, we weren't. No one was. We were just.
It was due next year.
It was due a year later.
But you saw that it speeded up.
Yes, you can see it. It's like if I changed that clock, if I sped it up, if I changed the time on that clock, and then you come in the next day and you notice an hour fast, you can come in any time and see that I've come in and sped up the clock. So. Now, when I say everyone was snoozing, there was one person who wasn't snoozing, and that was Steve Olney, who's the radio amateur I told you about before. And it turned out that he's got a setup, well, it's closed down now, but he's got a setup where he had some helical antennas in his backyard in Sydney pointing straight up, and Vela passed overhead, and he would get, for about, I think, 45 minutes to an hour's worth of signal from the Vela Pulsar. He can't see individual pulses by any means, but he would average over the entire hour and then be able to get a pulse and a time. And it turned out the glitch actually happened while he was observing, and he got the glitch in his data. So that was pretty amazing. For a radio amateur, that's.
Do you know his call, sir?
I can get it to you.
Oh.
Sorry, I don't. I know he's.
It's you,
And sorry, Steve, you're watching. I'm sorry, I don't know your call sign. He will be watching this.
but there's a goal for you for if you want to make yourself a name to be the second person in Australia to observe a pulsar. There's a little aim for you. Now, one other quickly thing that I'd like to mention is I mentioned that most of the elements that you can see around you here came from supernovas, and I looked for gold and platinum, what caused gold and platinum. So there was another fantastic bit of science that happened a few years ago with gravitational waves. They were looking at gravitational waves which were typically collisions of black holes, and they found this one which was a collision of neutron stars. Now, this is in galaxies far, far away, and so the dispersion measure I talked about that delays signals, radio waves essentially, and light and so on, because they're so far away, it delayed them by the order of days and even sometimes weeks. And so this gravitational wave, and gravitational waves don't get delayed at all, they arrive right on time. So this gravitational wave arrived, and they asked the gamma ray people, did you see something bright in your detectors? And they went, yes. And they said, right. And they did roughly worked out where the distance is, and they got all the radio telescopes on alert and said, go look at this. Then they asked the optical people, and they said, have you, in this rough area of the sky, did you find a little new bright point that wasn't there before? And they went looking and they found it. So they knew the galaxy, and then so all the radio telescopes then pointed at this galaxy, waiting for the signal to arrive from this neutron star collision, and they caught it. So it was multi-messenger astronomy. This happened a number of years ago, just a few years ago, and it was just a really, really nice bit of work. And out of that, they proved the fact that gold and platinum comes from neutron stars colliding, and that's why they're rare. There you go. I'll leave you with that.
Just going back to the pulses arriving from the pulsar. If I understood it correctly, the higher frequencies arrive earlier than the lower frequencies?
Correct.
What causes that?
It's the stuff between us and the pulsar. It slows it down. So it slows down the higher frequencies less. So there is stuff between, you've got 1,000 light years between, let's say you're the pulsar and I'm Earth. There's 1,000 light years between us. It is not a perfect vacuum. Okay? Sorry? Yeah. So you might have one atom per cubic, or one electron or whatever per cubic metre, whatever. But over a column, 1,000 light years long, that adds up. And it's enough to slow the signal down at lower frequencies.
Intrigued why it affects the lower frequencies more than the higher frequencies.
So what I suggest you do, go and look up dispersion measure. If you want to dive into the theory, that's what we call it. And it turns out to be incredibly useful for us because if you know the dispersion measure of, which is how much stuff there is in a direction, that can help you work out distance. Okay, so we can look at the dispersion measure of the Vela Pulsar, and that can give us a rough idea of distance because we know how much stuff due to other studies is between us in our own galaxy is there. So it's a sort of a handy guide to give us. So in pulsar distance terms, we talk about distance in terms of dispersion measure. We might know the exact distance, but we know it from the delaying of the arrival times of the different frequencies of the pulses. Okay, I've gone on a bit.
Thanks, Jim.
All right, thank you.